What if I told you time is not real? Right now, at this exact moment, time is moving faster for you than someone else on Earth. That shouldn't be possible. But it is. 1 second follows another. Steady, predictable, universal. But here's the strange part. The universe never agreed to that. Time doesn't tick the same everywhere. In some places, it crawls. In others, it nearly stops. And at the very beginning of everything, time itself may not have existed at all. This is the mystery of time in the universe. And the deeper we look, the less we understand it. Let's start with something you already know, but probably haven't thought about carefully enough. Right now, at this very moment, you are aging faster than someone standing on a beach at sea level. If you're watching this from a mountain, from an airplane, from the upper floor of a tall building, the clocks around you are ticking slightly faster than clocks closer to the Earth's surface. The difference is almost nothing. Fractions of a nanosecond over a human lifetime. But it's real, it's measurable, and it's not a glitch. It's how the universe actually works. This sounds impossible, but it's not science fiction. It's physics, and it starts with Einstein. In 1905, Einstein published his special theory of relativity, which contained a radical claim. No matter how fast you move, no matter where you go, the speed of light never changes. That single constraint forces something extraordinary. The speed of light never changes, ever. So something else has to give. And what breaks is time. Move faster, and your time slows down. This wasn't philosophy. It was physics, and it was testable. Then, in 1915, Einstein went further. His general theory of relativity proposed that gravity isn't really a force pulling you down, it's the warping of space-time itself. Mass bends the fabric of the universe, and that bending changes the passage of time. The closer you are to a massive object, the slower time moves for you compared to someone farther away. This is called gravitational time dilation, and it has been confirmed so many times and with such precision that the GPS satellites orbiting your head right now have to correct for it. Without those corrections, the navigation on your phone would drift by about 10 kilometers every single day. Time dilation isn't a curiosity, it's infrastructure. But let's push this further. What happens when you take gravitational time dilation to an extreme? What happens near the most massive, most dense, most violently warped objects in the universe? You get black holes. A black hole is what forms when a massive star collapses in on itself, compressing its mass into an almost infinitely small point called a singularity. Around that singularity is a boundary called the event horizon. It's not a physical wall. You wouldn't feel yourself crossing it, but it marks the point of no return. Beyond it, not even light can escape, and here's where time does something deeply unsettling. Now imagine your best friend falling into a black hole, and there's nothing you can do to stop it. You're safely far away, observing through a telescope. As your friend falls closer, something impossible begins to happen. They slow down. Not gradually, but dramatically. Second by second, they begin to freeze, until, from your perspective, they never cross at all. The light they emit shifts redder and redder, their image growing dimmer, until they appear to freeze at the edge of the event horizon. From your perspective, they never actually cross it. They just fade away, caught in an eternal almost. But from your friend's perspective, they cross the event horizon in a finite amount of time. They feel nothing special at that boundary. Their clock keeps ticking. They keep falling. Two people, two completely different experiences of time. And both are correct. Both are real. There is no privileged frame, no universal clock ticking in the background deciding who's right. Time, in general relativity, is local. It belongs to whoever is measuring it. This is already strange enough, but the mystery of time in the universe doesn't stop at black holes. It reaches back much further. It reaches all the way to the beginning. 13.8 billion years ago, the observable universe was compressed into an unimaginably hot, dense state. We call the event that followed the Big Bang. In the first fraction of a second, the universe expanded at a staggering rate. Matter and energy filled the cosmos. The laws of physics as we know them began to crystallize. And somewhere in that unfolding, time as we experience it started. But what does that actually mean? What was time doing at the very beginning? Here we run into one of the deepest problems in all of physics. General relativity, which describes gravity and the large-scale structure of the universe, breaks down at the singularity of the Big Bang. The equations produce infinities. The math stops making sense. And when physicists say the math breaks down, what they're really saying is that our understanding breaks down. We don't know what time was at the moment of the Big Bang. But here's the real problem. What happened before the Big Bang? That question might not even make sense. Because if time began at the Big Bang, then before doesn't exist. The word before assumes time already exists. It's like asking what's north of the North Pole. The question uses a framework that doesn't apply. Some physicists believe time didn't begin at all, not with a bang, but as something that slowly emerged. Together with physicist James Hartley, he suggested that as you trace the universe backward in time toward the Big Bang, time doesn't hit a wall or a starting point. Instead, it gradually becomes indistinguishable from space. Imagine time as the surface of a sphere. If you walk south along the Earth toward the South Pole, at some point the direction south simply ceases to exist. You haven't hit a boundary. The geometry has simply closed. Hawking proposed that time behaves the same way near the Big Bang. It doesn't begin, it rounds off. In this picture, asking what happened before the Big Bang is like asking what's south of the South Pole. There's no answer because the question has lost its meaning. But here's the problem. We still don't know how time actually began. In these cyclic models, time extends infinitely into the past through an endless sequence of expansion and collapse. Others suggest that our Big Bang was just one event in a much larger multiverse where new universes bubble into existence constantly, each with its own timeline. In some versions of string theory, and here's the most shocking idea of all, time might not exist at all. It emerges from deeper mathematical structures, the way temperature emerges from the motion of molecules. You wouldn't say a single molecule has a temperature. Temperature is a collective property. Time, in these theories, might be the same kind of thing. Something that only makes sense at a certain scale, something that dissolves when you look closely enough. This is where the mystery sharpens. Because when you zoom out and look at the universe on the largest scales, time reveals another strange behavior. It has a direction, and no one can fully explain why. Think about it. Almost every fundamental law of physics works the same whether time moves forward or backward. If you filmed two particles colliding and played the footage in reverse, the reversed version would obey the same laws of physics. The equations don't care which direction time flows. They're symmetric. And yet, we never see eggs unscramble. We never see shattered glass leap back onto a table and reassemble. We never see the dead come back to life. Time, as we experience it, has an arrow, and that arrow always points in one direction, from order to disorder, from low entropy to high entropy. Imagine a glass falling off a table. It shatters instantly, but you never see the pieces jump back together. That's entropy. Things fall apart and they don't reverse. Think about ice melting or a hot cup of coffee slowly going cold. Things naturally fall apart over time. The second law of thermodynamics tells us that in any closed system, entropy tends to increase over time. Things fall apart, energy spreads out, structure dissolves, and this, many physicists believe, is what gives time its direction. We remember the past because it had lower entropy. We can't remember the future because it hasn't been determined yet, at least not from our perspective within the system. But this explanation immediately raises another question. Why was entropy low in the past? If high entropy is overwhelmingly more probable than low entropy, why did the universe start in such an extraordinarily ordered state? The Big Bang should have been chaotic, random, disordered, and yet the early universe was remarkably smooth and uniform. The cosmic microwave background, the afterglow of the Big Bang, is the same temperature in every direction to within 1 part in 100,000. That uniformity represents an astonishingly low entropy starting condition, and we don't know why. Physicist Roger Penrose has spent decades thinking about this. He calls it the biggest unsolved problem in cosmology. The initial conditions of the universe seem fine-tuned for low entropy, and no current theory explains this convincingly. Penrose himself proposed a model called conformal cyclic cosmology, in which the universe goes through infinite cycles. At the end of each cycle, as all matter decays and black holes evaporate, the universe becomes so uniform and empty that it becomes indistinguishable from a low entropy state again, and a new Big Bang begins. In Penrose's view, the arrow of time is not a one-time event. It resets. The cosmos breathes, entropy rises, peaks, and then the geometry of the universe folds the ending into a new beginning. It's a beautiful idea, and it remains deeply controversial, but it captures something important about the mystery of time. Every answer opens a new question. Every explanation rests on an assumption we can't yet justify. And there's another layer to this puzzle, one that involves the most successful and most disturbing theory in all of physics: quantum mechanics. At the scale of atoms and subatomic particles, the universe doesn't behave the way we expect. At the smallest level, reality doesn't even decide what it is until you look at it. At the smallest level, reality doesn't choose what it is. A particle can be here and there at the same time. Only when you look does it decide. This process, sometimes called the collapse of the wave function, introduces something deeply asymmetric about time. Before measurement, the future is open, probabilistic, undefined. After measurement, the past is fixed, determined, recorded. This asymmetry feels like time. It feels like the flow of moments from possibility to actuality. But here's the problem. The fundamental equation of quantum mechanics, the Schrödinger equation, is perfectly time-symmetric. It doesn't prefer forward over backward. The arrow of time, the sense that the past is fixed and the future is open, is not built into the equation. It's added by hand, through the act of measurement, through decoherence, through our interaction with the system. Some physicists interpret this to mean that time's arrow is not a property of the fundamental laws at all. It's a property of us, of how we observe, of how we participate in the universe. Time, in this reading, is not out there, it's here. It's in the relationship between the observer and the observed. This idea connects to an even more radical proposal that has gained traction in recent years: Several approaches to quantum gravity, the long-sought theory that would unify general relativity and quantum mechanics, suggest that time is not fundamental. In the Wheeler-DeWitt equation, one of the earliest attempts to write a quantum equation for the entire universe, time doesn't appear at all. The equation describes a static, timeless cosmos. Change, flow, sequence, before and after, none of these are part of the fundamental description. They emerge, somehow, from the quantum relationships between parts of the universe. Physicist Carlo Rovelli, one of the architects of loop quantum gravity, has taken this idea seriously. In his view, time emerges from thermodynamics and our coarse-grained perspective on reality. We experience time because we can't track every microscopic detail of the universe. We see averages, patterns, flows, and from those flows, we construct the sensation of time passing. If we could see every particle, every quantum state, every interaction all at once, Rovelli suggests, time would disappear. There would be no flow, no direction. Just a vast network of relationships frozen in a timeless mathematical structure. This is not science fiction. This is the frontier of theoretical physics. And whether or not Rovelli's specific proposal turns out to be correct, it reflects a growing suspicion among physicists that time, as we experience it, is not the deep truth. It's the surface, the shadow, the story our brains construct to make sense of a reality that may not, at its deepest level, have anything to do with clocks or moments or sequences at all. But let's step back from the edge of theory and return to the cosmos, to what we can see and measure, because even observational astronomy confronts us with the strangeness of time. When you look at the Andromeda Galaxy through a telescope, you're not seeing it as it is, you're seeing it as it was 2.5 million years ago. That's how long its light took to reach you. The sun you see in the sky is 8 minutes old. The most distant galaxies we've ever observed are so far away that their light has been traveling for over 13 billion years. We see them as they were when the universe was in its infancy. In a very real sense, the deeper we look into space, the further back we look in time. The universe is its own time machine, and our telescopes are not just instruments of space, they are instruments of history. The James Webb Space Telescope, launched in late 2021, was designed specifically to see further back in time than any telescope before it, and what it found challenged expectations. Galaxies forming far earlier than models predicted. Massive, well-structured galaxies existed just a few 100 million years after the Big Bang, when the universe should have been too young, too chaotic, too hot for such things to have assembled. These observations don't overthrow the Big Bang theory, but they complicate it. They suggest that the early universe evolved faster than we thought, that time, or at least what happened within it, moved differently than our models assumed. There's a strange poetry to this. We build machines to look deeper into the past, and what we find is that we understand even the past less well than we thought. Time hides its secrets not only in the future, but in its own history. And then there is the question that perhaps troubles physicists more than any other when it comes to time. The question now: what is the present moment? In Einstein's relativity, there is no universal now. Two events that are simultaneous for one observer may happen at different times for another observer moving at a different speed. The present is not a shared cosmic moment, it's observer-dependent. In the block universe interpretation of relativity, which many physicists take seriously, past, present, and future all exist equally. The entire history of the universe, from the Big Bang to the heat death, is laid out like a frozen four-dimensional block. Nothing flows. Nothing passes. The experience of now, of this specific moment reading these specific words, is just one slice of a vast, unchanging structure. If that's true, then what we call the flow of time, the sense that we're moving from the past into the future, is an illusion. A powerful, inescapable, deeply felt illusion, but an illusion nonetheless. Our brains are wired to experience time as it flows. Our memories, our anticipations, our emotions, all of them depend on the sensation that one moment follows another. But physics, at least in its current form, does not require this sensation to be real. And yet, we feel it every moment of every day. The cool morning air gives way to afternoon warmth, the slow turning of the seasons, the way a song builds toward a chorus and then resolves. Time feels real, it feels directional, it feels like the most basic feature of existence. And maybe that subjective experience is telling us something important, something that the equations haven't yet captured. Maybe the flow of time isn't an illusion to be explained away, but a clue pointing toward a deeper theory we haven't yet found. This is where we stand, at the intersection of everything we know and everything we don't. Time is real enough to regulate the orbits of planets and the ticking of atomic clocks. It is strange enough to slow near black holes and dissolve at the Big Bang. It is fundamental enough to shape our every experience and yet possibly emergent, possibly not part of the ultimate architecture of reality. We've spent centuries measuring time with increasing precision. We've built clocks that won't lose a second in 15 billion years. And yet, we still cannot answer the simplest question a child might ask. What is time? Perhaps that's the most honest thing we can say. The universe has given us enough clues to know that time is far stranger than it appears. It has given us enough evidence to know that our intuitions are unreliable. And it has given us just enough mystery to keep searching. Every telescope we build, every equation we write, every thought experiment we follow to its logical end, they all bring us closer, not to a final answer, but to a better question. And maybe that's what time really is. Not a river, not an arrow, not a dimension, but the universe's way of asking us to keep looking, to keep wondering, to keep standing at the edge of what we know and staring into the darkness beyond. Because that darkness is not empty. It is full of everything we have yet to understand. Maybe time isn't something we live in. Maybe it's something we create. And if that's true, then the biggest mystery isn't the universe, it's us. And perhaps that makes the search even more beautiful.